And there we go. Okay, can you hear me? Very good. All right, so this talk, coding like Frankenstein. Obviously, that's something, when I was asked to do it, it turns out this is actually something I know a lot about. I have done some historical research, and really this topic should be called, hold on a second. Where is my gadget? There we go. This talk should really be called Dr. Frankenfunctor and the Monadster. So this is a very different topic from the last one. This is going to be about monads, I'm afraid. So, Dr. Frankenfunctor, I'm sure you know who Dr. Frankenfunctor is, and if you don't, I will explain it. My name is Wlaschin. My website is fsharp4funandprofit.com. I'll be using F-sharp code examples here, but these are actually the basic principles. So the principles apply to any functional programming language. You can do it in C# or Scala or even JavaScript or whatever. It's not really about the code. I'm going to show code samples, but I don't really expect you to understand the code. I just want to give you an idea of how things work. And I'm also going to go through a lot of stuff very quickly. And again, you can't really possibly understand it, I don't think, in an hour. So it's really just to get the concepts, just to even introduce you to some of these concepts and to show you they're not really scary. Really, there's no way that you can really understand all this stuff so quickly. So I'm just going to whiz by very quickly and just going to give you, it's like one of those tour buses that goes around a city and you see, the Eiffel Tower for 5 seconds and you see something else for 5. It's that kind of thing. It's a very, very quick trip around all the topics. So I have to warn you before I start, this talk does contain certain information that might worry people. First of all, it's got a gruesome topic. So it's got the monadster and it's got kind of zombie things in it. So just to let you know, it's got some very strained analogies between zombies and monads. And it does have a discussion of monads, so if that worries you too, that's, some people have to block their ears when they hear that. So seriously, if you are sensitive to like zombies and stuff, I know some, no, seriously, I mean, if some people don't like that, then, just let you know in advance, this talk does have that in it. I'll be talking about dead body parts and things. Yuck. Okay. All right, so if you're doing functional programming, the main way that you build more complex things out of smaller things is using function composition. And it's really a fantastic thing, and I will demonstrate how it works. Here is a function. It has an input and an output. And all functions have an input and output. That's very easy. And if you have two functions and you want to kind of glue them together to make a bigger function, you just connect the output of one thing to the input of the other thing, and then you kind of glue them together, and now you get a bigger function. So that's great. That's function composition, and it's brilliant. But there's a problem, because not all functions are actually that simple. Sometimes you have a function which has two outputs, one input and two outputs. Or sometimes you have a function that has two inputs and two outputs, or sometimes it has two inputs and one output. And when you try and glue all these things together, they don't fit. They're all the kind of wrong shape, So each function has a sort of shape. The first one is kind of a Y shape, and the other one is, a linear shape, and others. So you've got all these different shapes, and you're trying to fit them together, and they don't fit, right? And that's the problem with when we start having interesting kinds of functions. So how do you fit them together? Of course, the answer is monads. Monads is the answer to everything in functional programming, which is why people go on about it all the time. So I'm going to try and explain why. But what's that got to do with Dr. Frankenfunctor? Well, if we think about the history of monads, so monads were first talked about in 1990 at a computer conference. And of course, this was the result. People freaked out. Very bad things happened. I don't really want to talk about it because it's too nasty. But it was a bad thing. And of course, this kind of virus spread around, and you had people starting writing monad tutorials, and lots of monad tutorials. Very dangerous thing. It's really spreading around like a virus. But what people don't know is actually 200 years ago, Dr. Frankenfunctor invented monads. Okay, so we think of monads as a recent thing, but it turns out that Dr. Frankenfunctor when he created the monadster, he actually invented functional programming, and not many people know this. So this is sort of the secret history of monads. So you probably all know about the monadster, right? Everyone knows the monadster. Here is the first gruesome slide. Okay, the creature, the monadster, was built from bits of bodies, and it was assembled in a lab. Right, all the bits were glued together, and lightning struck, vital force was created, and the creature was animated in one instant. Right, and we all know this story, and this was the result. This was the monadster, and you can tell it's the monadster because it has the mark of the lambda. This is if you see something like this and it has a lambda in front, then you should run away very fast. So everyone knows that story, and we know this is a terrible thing that happened. But the question is, how was it actually done? What were the techniques that Dr. Frankenfunctor used to create the monadster? And as it happens, I've devoted many years of research into this matter. I've gone to secret papers, and finally I can actually reveal the results of my research and tell you how Dr. Frankenfunctor did it. And this is still relevant. The techniques he used are still relevant for modern day programming. We can learn a lot from what he did. Now, he was working with physical body parts, obviously gluing things together in his lab, but a lot of those techniques can actually be applied to software, believe it or not. Okay, now we have to watch out that these are very powerful techniques, and they can be used for good and evil. So be very, very careful how you use them. Okay, so what was in his toolbox? What were the techniques he used? Well, the first thing, as I said, he invented functional programming, and he modeled everything with pure functions. And I'll talk about why that was very useful for him. And then he did the thing, wrapped a function in a type, and that's a kind of strange thing to do, and I'll show you how that works. And then he had various ways of transforming these body parts into other body parts, combining two body parts into one, combining live and dead body parts at the same time, which is kind of yucky. And then, having these part-creating functions which he managed to glue together to make more part-creating functions. So a lot of complicated stuff, and then a general way of combining any number of body parts together. So, like I say, he was working with a lab, but these techniques actually still amazingly apply to modern software. So again, I don't expect you to remember all this stuff. It's really a rapid overview of all these techniques, and you can go and read more about it later on and try it for yourself. So, just to demystify it, give you an overview. All right, so what was his first technique? So his first technique was modeling with pure functions. So here is his dead body part. This is a leg, and he wanted to make a live leg. All right, and he needed to give it this extra vital force with the lightning and everything to make it become alive. So it wasn't just the input to this function, was not just this dead body part, it was also this extra bit of lightning, right? So if you want to model this as a function, and by the way, don't try this at home, okay? Don't connect a lightning thing and try and make body parts, it's not good. So he created this as a function, and the function had two inputs. So the function had the body part that he was doing and the lightning, the vital force, that was the input. And then the output of the function was now the live body part, and also the remaining body force. So there's two inputs, two outputs, and when you create something like this, you use up a little bit of vital force. So he started off with, say, 3 units of vital force, and he was left with 2 units afterwards, right? Because it takes work to create live things. So this is a pure function. There is no globals. There's no global variables keeping track. There's no mutation. There's just inputs and outputs, and like I say, it's totally a pure function. But there's a problem with these pure functions, and I'll talk about 2 of them. The first problem is when you have more than one of these things and you want to connect them together, you need to remember how much vital force you have left, because you've got 2 units after the first thing, and you need to take those 2 units and feed it in, and then you only have 1 unit the next time, and so on. But you can't just run them all at once. You have to feed the vital force throughout all these functions. So how do you connect these functions together? That's one question. And the next question is, you've got these live body parts now, and how do you glue those together, right? You need to connect these functions, the output of these functions in some way to build up a bigger piece. So he invented this, in order to make this problem easy to manage, he created this function, and he wrapped it in a type. And he created this thing which we call it Schoenfinkeling. Anyone know what Schoenfinkeling is? No? So Moses Schoenfinkel is the guy who invented Schoenfinkeling. And he's a real person. No, he's a real person. The only problem is, actually, we don't call it Schoenfinkeling. Even though he invented it, we don't call it Schoenfinkeling. We call it currying, because this guy Haskell Curry got the credit. So, unfortunately, Moses Schoenfinkel, we don't call it Schoenfinkeling. It's just a shame, really. So, currying is what we call this technique. And what is currying? So, everyone, a lot of people have heard of currying. Let me tell you what currying is. So, currying is a way of taking a function which has two inputs, or more than two inputs, and turning it into a function that has one input. And how do you do that? Well, you use the fact that functions can return other functions, right? Functions are things in functional programming, so you can return another function. So after currying, we have a function that has the A input, and that spits out a new function. And that new function has the B input, and then that function also spits out the C input. So now we've turned a two-input function into a chain of one-input functions. So that's all that currying is. Very simple. And I'll actually give you a little demonstration. So this is F-sharp code. Like I say, don't worry too much about the syntax. But this is the F-sharp code for creating a lambda. Now, if you were using C#, you wouldn't need the fun keyword. You just have the thing, and you would have a double arrow rather than a single arrow like this. But otherwise, it's similar in C#. So I'm just creating a function called add1. And if I want to use it, I just say add1 of 2, and that's 3. Okay, so that you're probably familiar with doing that in C# as well, or most programming languages have lambdas. But what you can do is you can pass a parameter into this lambda. So I'm going to create a lambda which has x as a parameter, and it's going to bake x in as into the lambda. So the lambda is going to have the x baked into it. So the lambda still needs a y parameter, but the x is kind of hard-coded. So this time, if I say add 1, I can just pass in 1, and that bakes in the 1 into the lambda. So now we have an add 1 function, and we can call it, we can say, same thing, 3 is add 1 of 2. But what's cool is we can not bother to create the intermediate add 1 function, we can just inline it, right? So we add and put the 1 and then the parentheses, right? Or we can even get rid of the parentheses altogether and say add 1 space 2. So when you look at code like this in F# or in Haskell or OCaml or other languages, you think this is a 2-parameter function, but it's actually two 1-parameter functions. So it's add 1 is the first function, and then passing 2 to that is the second. So in F#, all functions are curried by default, which is really nice. And this is one of the reasons why functional programming languages actually have spaces as the parameters. You might think, why don't they write functions like normal people with commas and parentheses and stuff? It's because these are actually multiple functions in a row, separated by spaces. Okay. So how does currying apply to our become alive function? So we've got two inputs, and the dead part we already have. We have that right now, but the lightning, the vital force, we don't have that. We'll have to wait for a storm. We'll have to use lightning maps to wait for the lightning to come near us, and then we can set it up. But we can do a lot of stuff without even having the lightning. So what we're going to do is use the dead part to create a function, right? So before we had this, and afterwards we have that. So that is currying right there. And then what we're going to do is we're going to give that function a name. We're going to call it m of something, and it's m angle brackets. The thing it returns depends. It might be a part A, it might be a part B, it might be a leg, it might be an arm, something. So it's a generic thing, just like a generic list or a generic other type. This is why I've got the angle brackets. We give it the letter M for monadster. And that M thing, it's not returning, when it says it's an M of a thing like an arm or a leg or whatever, it's not an actual arm or leg, it's a potential to be an arm or a leg, right? We still need to provide the vital force, the electricity, to make it into something. So it's basically a little tiny program that will make, it's a promise, if you think of it that way, that will make something when you give me the vital force to do it. But once we've turned that thing into, we give it a name like an M thing, we can start writing recipes. And we say, okay, here's the dead part, and it will make, I can actually make a live part, or a promise of a live part, an M of a live part. So again, this M thing is not a real thing, it's a potential thing. Okay, I hope that makes sense, yeah, to everyone? Okay, I know I'm kind of whizzing past very quickly on this. So we've got this thing that's a potential live part. How do we actually make an actual live part from it? So we need to run it. We need to actually provide the extra vital force to actually run this thing to make the actual live part. So because remember, if you look inside it is actually a function that needs the vital force to be run. So when we run, so we're going to have a special thing that runs one of these M things. And we give it, when we run it, we also give it the vital force, and that gives us finally we get the real thing. But we run it at the very, very end. We only do the run when the lightning is just about to strike, right? We can spend weeks setting everything up, and then when the lightning strikes, then we can actually do the running. But up to that point, we can't run it because we don't have the lightning to do it with. All right, so let's look at some code. Again, don't worry too much about the syntax. Can you read that at the back? Yeah, hopefully. This is F# for creating types, so we're going to create a dead left leg and a live left leg, and then we're going to create, so this is the function for actually creating, this is how you'd actually create something from scratch. So we're going to take the label, we kept track of where the leg came from, which person it came from, so there's a label attached to the leg, and then we create our little become alive function. The become alive function needs some vital force. We then take a unit of that vital force, and we get 1 unit, and we've got some remaining vital force that we need for next time. Then we create the actual live thing with that vital force, and then we return the live thing and the remaining vital force. That's the output of the function, and we just return it as a tuple here. And then we wrap that whole function up with this M thing. Okay. So again, the point here is not really to understand the code in detail. The point is that it's really just like 4 lines of code to make one of these M things. It's not a complicated thing at all. And then we want to use it when we actually want to run the thing. Here's a real dead left leg called Boris. And we make a leg M thing. So that's something we can do right now without having the vital force, without having the lightning available. We can create one of the M things right away. And then when there is vital force available, let's say we have 10 units of vital force available, then we can actually run it like this, run M, it's running it with the M thing and the vital force, and the output is a live leg, which has 1 unit of force in it, and then also the remaining force is now 9 units left. We used up 1 unit to make it. So again, don't worry too much about the code, really it's just to show you that the concepts may be complicated, but the actual amount of code is like a couple of lines of code. It's really not a lot of code to write. All right, so we have this concept of M things, potential things, promises of making things. How do we actually use these things? Because sometimes that's not good enough. So let me give you an example of when we need to transform these things into other things. So here, Dr. Frankenfurter, he wanted to have an arm, but it turned out that all he had was a broken arm, all right? So he had a dead, broken arm, and he wanted to make a live, healed arm. And how could he do that? So that was his next challenge. Well, it turns out that he's a doctor, and he knows how to heal broken arms. So there is actually a function that we have that will heal a broken arm. The only problem is it works on live broken arms only, okay? It doesn't work on dead things, because you have to use live, treatment. So he has a function which works on live things, but he starts off with a dead thing. So how can we put all these pieces together and glue them together to make something that's useful? So here we have our dead thing over here. We have our live thing over here. How can we get from one place to the other? Well, okay, so let's say I'll use the heal thing, and I'll go from, we make a healed dead one. No, can't do that, because the function only works on live things. All right, well, let me create a live thing and use the function on the live thing. Well, the problem with that is that I can't create a live thing directly. I can create an M of a live thing. I can take the potential live thing or a promise of a live thing, but I can't actually create the live thing yet. So that doesn't work. So what I can do is create an M of a live thing. But I now need to turn an M of the broken thing into an M of the healed thing. And I can't. That heal function only works on normal things, it doesn't work on m things. So what we need to do is have a special function that works on m things. Right? If we could turn an m of a broken thing into an m of a healed thing, that would solve all our problems. So where are we going to get that function from? Well, here we go. Here's our function that we have. We have a function that turns broken things into healed things. We want to have a function that turns m of broken things into m of healed things. How do we get from the bottom function to the top function? That is where map comes in. So if you hear about map in functional programming, all that map does is turn one kind of function into another kind of function. And here's a kind of complicated diagram, unfortunately. Trying to explain this in pictures is quite hard. But if on the left-hand side, what you see is there's basically the normal world of normal things, and then there's the world of m things above it. And what we're doing is we start off with a function in the normal world of normal things, and after we've done map, we have a function in the world of m things. So it's the same function, but it's been lifted. We use the word lifted to move it into this world of m things. So map's a very important function. And I'll just show you the code quickly. Here's some more things. Here's the type definitions, the class definitions of the broken arm and the unbroken arm and the healed arm and all of those things. But here's the main thing. To heal a broken arm, we start with a broken arm, and we basically get the data out of it and we create a healed arm. So that's how we can, our function that works with the normal things, it just takes the data out of the broken thing and makes a new thing out of it. That's how we heal it. But that's not the map function. So the map function looks like this. The map function has two inputs. It has a function that you're going to do the transformation with, and it has your m thing. And again, you have your become alive, your inner function, which in this case is a transformation function. It has some vital force that goes as the input. You basically get the body part, the original body part, by running the thing with the vital force that you have. You then transform the body part using the function that you were given, and then you return the transformed part and the remaining vital force. So by doing this, and then of course you wrap that inside function in this m thing. So again, it's complicated. It's kind of complicated code to understand, but again, I just want to show you that you can write a map function, even though it sounds like a complicated thing. It really is a couple of lines of code to write these things. And if you look at the signature, this is an F-sharp signature, and the little tick A means a generic type. So this is in C#, that would be angle brackets A and angle brackets B. So this is a generic function. The input is a function that takes normal things of A to a normal generic B. And the output of the function is, you can see, it takes a M of a generic A to an M of a generic B. And that's what maps always have, that signature. Starts with an input function and spits out another function, which is a lifted version of that same function. All right. And then we use it again. So let's say we want to do it. We use mapm to take our normal function and turn it into the m version. And then we can run the m version on the m of the broken arm. We get an m of a healed arm. And if we run it again, we get this output. And again, we've used up 1 unit, and we get 9 units of vital force left. So again, don't worry too much about the code. I just want to show you that you can actually do a lot of manipulation in literally 10 lines of code. If you didn't have all the comments, the code would be a lot shorter. So map is, the reason why map is so important is it's not just for m things. Map works for all sorts of things. So you have list map, and you have option map, and you have anytime you have a generic thing, there's a map for it that turns a function in the normal world into a function in the elevated world. So here's an example for the world of options. So there's the world of options, optional things, and down here there's the world of normal things. And so there's a corresponding, for everything in the normal world, there's a corresponding thing in the optional world. So there's an int down here, and there's an optional int up here. And there's a string down here, and there's an optional string down here, and so on. And what happens is typically when you're programming is, for some reason you return an optional int, is some function. But then you want to process that int and you come down to the normal world to process it, and then you go back up again, and you go back into the optional world, then you come back down into the normal world, and you go back up into the optional world, and you come back down into the normal world. And if you have this kind of zigzag pattern going up and down, that basically means you're doing it wrong. Okay? You don't want to be going up and down. What you want to be doing is going up and then staying up. You want to basically stay in this world, in the higher world, as long as possible, and then finally come down at the end. Right, that's the right way to do it. So this is the kind of functional programming idiom, the way of doing functional programming. So how can you stay up in this optional world, right? So this is the challenge. So again, let's use a little example. Let's say you just want to add 1 to something, right? And that works in the normal world of ints down here. Now, when people start functional programming, they typically write code like this, which is like, oh, I want an optional version, so let me see if the optional version is actually something, and if it's something, I'll unwrap it basically, and then I'll apply my function, and I'll wrap it back up again. You know, if you see a lot of code, I mean, fair enough. When you're starting out, it's easy to write code like this. So I'm just going to encourage you not to write code like this, because again, what you're doing is you're unwrapping, you're coming down, and you're doing something, and you're wrapping it back up again. What you really want to do is take your add 1 function and move it to the top, right? And again, how do you do that? You use option map in this case. So option map basically takes any kind of T type to any kind of U type, and it turns it into an option T to an option U. So any kind of function down here, it turns it into a function up there. And again, that's called lifting. That's why people call that lifting, because you're moving it from down here to up here. So add 1, if we do a map, we get an optional add 1. And if we see the difference between the code, if we take the normal version, we pass it 2, we get 3 as the answer. And in the optional version, we take sum 2, which is something, and we get sum 3 back. So we've turned a function that works in normal things into a function that works in optional things. And here's some code to demonstrate. Now, this option map will work for anything. So here I have my heal broken arm function, and if I run it through option map, I get something that works on options. So I can have an optional broken arm, and it turns it into an optional healed arm. And here's my addition function, right? And typically what people do is, rather than creating special add 1, an optional version of add 1, you just inline it like this. So this last one is what people typically use. You just say take the option and just pass it in to the map version of add 1. You don't normally create a special intermediate function. I'll put the slides up afterwards, by the way, because I know I'm whizzing through them, and you probably want to have a chance to look at this code. And here's a version of list map. So list has a map as well. And if you're using C#, that's the equivalent of select. Right, so map in functional programming is the same as select in LINQ. So here's list map, and so if I apply it to the heal broken arm, and now I have something that takes a list of broken arms and turns it into a list of healed arms. Right, so that's what list map does there. And again, if I use it on the add 1 function, if I pass in a list of things, it adds 1 to everything in the list. So that's map. All right, so that's quite a lot of talking about map. Okay. Now, what happens if you have 2 things you want to combine together? So let's say, back to the gruesome analogies again. Let's say that we have 2 pieces of an arm, having a lower arm and an upper arm, and we want to create a complete arm out of this. Now, as it happens, Dr. Frankenfunctor knows how to do arm surgery as well, and he can take these 2 arm pieces and glue them together. But again, he can only do it for live arms. He can't do it for dead things. So here we have our situation. We have 2 dead things down here. We have a live thing up here. How do we get from this corner up to this corner? Again, we can't do it on the bottom level. We can't at the normal level of dead things. We can't do arm surgery because it doesn't work. You say, okay, we'll turn everything into a live thing and do the arm surgery. But again, we can't create live things directly. We can only create potential live things, the M of live things. So what we want to do is move everything into the world of M things and do the arm surgery there. But the normal arm surgery function won't work. We need a special arm surgery M, an M version of arm surgery. How do we get that? again, we have a 2-parameter function down here. We have the m version of the function up here. How do we get from the bottom one up to the top one? Well, this is a 2-parameter function, not a 1-parameter function like the previous one. But luckily, there's something called map2, which is a 2-parameter version of map. So just the same as map, except any kind of 2-parameter function, it lifts up to a 2-parameter function up here. So very useful. And again, you can see it in all sorts of things. It's useful for options and lists and so on. So any kind of function down here can be moved up to here. So these are generic functions, right? Once you've written this map and this map2, you can work for any kind of m thing, because these are completely generic over all kinds of m things. All right, next technique. Combining live and dead body parts. Okay, this is particularly nasty. So let's say that you have a dead brain and you have a head, an empty head, and you need to create a live head. So how do you do that? Well, the function here is he's not doing arm surgery, he's doing head surgery. But with the head surgery, he doesn't need the second thing to be live. The head is already there. He just needs to make the live brain and put it in the head and make the live head out of it. So it's the same thing we've seen before. We can't use the live things. We can't create a live thing directly. We're going to have to create an M of a live brain, a potential live brain. So we have to move everything up to the level of M things. But now we have a problem because we have an empty head. So the brain can become a live, an M of a brain. We know how to do that. But how do we take an empty head and make it into an M of an empty head? We're not actually adding any vital force. We're not transforming it in any way. All we want to do is like take it from down here and move it right up there. And so what kind of function can we use for that? It's not map. It's not something like that. The function is normally called return. Sometimes it's called pure. All it does is take something in this world and just move it right up to the other world. Okay, it doesn't transform it, doesn't do anything, it doesn't use any vital force. It's literally just a kind of a copy, but it copies it into this higher world. So once you have the return function, we can take the empty head and move it into the M world, and then we can have an M version of the head surgery, just like before, by using map2. So now we've combined two techniques. We're using return to move something up, and then we're using the map2 to move another function up. So you can see that we've kind of building up a repertoire of ways of moving from this lower world up into this higher world. And we're working now at the higher world as much as possible. So that's what these techniques are all about. And again, you can think of it, if you think of it in layers, you've got a normal thing down at the bottom, and when we do return, it becomes an M of a thing over there. So it's not a function, it's just mapping normal things. And again, useful for all kinds of elevator types, so lists, options, all that stuff. All right, next technique, M generating functions. Now we're getting a little more complicated. I know you might think it's been complicated so far, but now it's going to get really complicated. So like I said, if you're getting lost, I know I'm whizzing through this really quickly. The point is really not for you to completely understand all the stuff. It's just to get a vague picture in your head and sort of demystify it. Okay, it's just to realize it's actually not that complicated. So that if you actually do go and look at it afterwards, hopefully it'll make a little more sense with these analogies. So, what's an M generating function? Okay, so the next piece. Poor old Dr. Frankenfunctor, he keeps having to take all these things and work with them all the time. It's hard work. So he's got this dead heart here. And what he really wants is a beating heart for his monadster. The monadster needs a beating heart. How can he create a beating heart? Well, it turns out that beating hearts are not easy to create. There's actually 2 steps in creating a beating heart. The first step is to create a normal live heart. That uses a little bit of vital force just to turn it from a dead thing into a live thing. But once it's a live thing, you then need to make it beat as well. And that also is another step. That also uses some vital force. So Dr. Frankenfunctor has these 2 functions. He has a function that turns a dead heart into a live heart, an M of a live heart, a potential live heart. Because remember, he doesn't have any electricity, right? All these things are just potential things. They're promises of things. He can't actually create anything live until the lightning strikes. So he can create a potential live heart. And if he has a live heart, he knows how to create a beating heart. But again, a potential beating heart, because he needs some extra electricity to do it. So he's got these two functions, and each of these functions take a normal thing and turn it into an M thing. Now, to take a dead heart and turn it all the way into a beating heart, he's going to have to chain these two functions together somehow. He's going to have to go through this first function and then take the output of that and go to the second into the second function. So the problem is these functions don't chain together very well, because the output of the first function is an M thing, but the input of the second function is not an M thing, it's just a normal thing. It's just a normal live heart. So they don't chain together. We can't compose these functions at all. And that's a problem. So the types don't match up. So how can we fix this problem? Well, if the input to the second type became an M thing, right? So there's it without an M, and there's it with an M. If we could turn it into an M thing, that would solve our problems, because then we can actually connect the output of one to the input to the next, right? So this is what we need to do. We need to somehow take the live heart thing and turn it into an M of a live heart. All right, so look at it from, just isolate that function on its own. So the original function we have takes a heart and turns it into an M of a beating heart. And what we want to do is have the input also be an M thing, right? So we've changed it from the original function into a function that works purely on the M level. And that transformation function is called bind. So what bind does is take an M generating function and turn it into a function that works entirely at the level of M's. So again, you can see there's a pattern here. We're always trying to move everything to the level of M's, to kind of horizontal M things. And once we've got all these M things and they're all horizontal, we can glue them together nicely. So these M generating things, I'd like to think of as sort of diagonal functions, because they start off in the normal world and they kind of go up diagonally to the M world. Right, so they're kind of a diagonal function or an M generating function. But after we've done bind, the first bit, the input, has moved up to the M level as well. So now we have a horizontal function. So the diagonal function has turned into a pure horizontal function. And this is what we want. We want everything to be these horizontal functions. So that's why bind is so useful. So let's look at some code. Yeah, and don't care about how you actually make a live heart. So this is the thing that makes a live heart. And there's the signature. It takes a dead heart and makes it into an M of a live heart. Like I say, this code is whizzing by very fast. It's really just to give you a concept of really how little code it is. So the concepts may be complicated, but the code is quite simple. So here's something which takes a live heart and it makes an M of a beating heart. And I need to glue these two things together. So here we go. We're going to, first of all, we're going to convert our diagonal function to our horizontal function. And we'll use that bind M. There's the bind M of the original version. And now here we have the horizontal version. And then what we can do is we can then flow the data through the entire chain of functions. So we start off with the dead heart, right? And then we're going to turn it into live heart. And after we've done that, the output of this step will be an M of a live heart, right? And then now we can take that and feed it into the next step, which is the beating heart. So it's and the output of this step is now an M of a beating heart. So this is we've now successfully managed to chain these two functions together. And if we run them, we get the output here. But what's interesting is the vital force now is 8 units. So it's actually figured out that we've used 2 units of vital force. The first step used a unit and the second step used a unit. And it's been keeping track of this. So what's kind of cool is that we're keeping track of how much unit of vital force is used up, but it's not in our code anywhere. There's no global variables that says how much vital force you've used. So this, what's kind of cool is the code is about the superficial things, like I'm taking this and I'm transforming it into this and then transforming it into this. And behind the scenes, the vital force is being tracked, but it's not messing up our code anywhere. And that's very cool. So we're sort of threading the vital force through all our code in an invisible way, which is, I think, is really nice. And these are pure functions. Remember, I haven't done any mutable functions. I haven't done any global variables. These are all pure, which means they can be extracted and refactored and split across multiple modules and classes and stuff. It's not like an object where you have some sort of state that mutates inside the object. And it means it's really hard to pull a method out of that object and put it somewhere else. But because these are all pure functions, I can actually have them scattered around because every single one is completely independent. Right, so bind, this thing of taking a diagonal function and turning it into a horizontal function, is really, really important. Along with map, bind is sort of the most important function in the most important concept in functional programming. And again, why is it useful? Because often you have these diagonal functions, and here that we're in the world of options, all diagonal, and what we want to do, they're no good to us. These diagonal functions are useless. Really what we want is a bunch of horizontal functions. So we use bind to make that one horizontal. We use bind to make that one horizontal. We use bind to make that one horizontal. And now we have a whole bunch of horizontal functions. And we can stay up in this world and do everything up in this world before we come down. So horizontal functions are good. That's the way to do it. And finally, we have this. We can take this technique and apply it to all sorts of things. So sometimes you have a 3-parameter function that you need to move up, or a 4-parameter function you need to move up. And rather than having to write special map 3 and map 4 and map 5, there's a really nice technique which I'll just show you quickly. So let's say that we have our complete body, okay, and the body has 2 left legs for some strange reason, and it has a left arm and a right arm and a head and a heart. Okay, so our body, this is our body definition. Okay, there's 6 pieces. And we're going to have some function that creates a body, and it's going to have 6 parameters. Right, and finally, after it spits out a live body. So we have a 6-parameter function, and we know where this is going. We won't be able to use the 6-parameter function down here. We'll have to turn it into a 6-parameter function up here. We're going to need a map 6, right? But no, it turns out there's an easier way. We don't need to have a map 6 function. And this is uses this technique called apply. So apply is a kind of a strange function. When you first see it, you think, how is this possibly useful? What apply does is take a function that's wrapped in an M and kind of pull out the first parameter. So if you have a function which is an A to B function and it's wrapped in M, when you do apply, it splits it into an M input and a B output, an M of an A output and an M of a B output. And if you have a more complicated one, so here's an ABC function, it pulls out the A and leaves the BC. And if you have an ABCD function, it pulls out the A and leaves the BCD as a 2-part. So you think, well, how can that possibly be useful? It's a very strange kind of thing. Is it really relevant at all? But what you can do is you can keep using it over and over again. So let's say you have this ABCD, you do apply and you pull out the MA, and you've got this BCD left. And then you do apply that, and that pulls out the B, and now you've got a CD left. And then you do apply that, and now you've got the C pulled out, and now you've got the D pulled out. So what you've done is you've turned a function with all these things, and you've turned it into a series of MA, MB, MC, MD. So let's see how it works in practice. Here is our ABC input, 3-parameter function, and it spits out some kind of result. And in the normal world, we'd pass in these 3 parameters and get back a result. But we know we're going to have to turn everything into M things. So the first thing we do is we take our normal function and we lift it into the M world using return, which we talked about earlier. And then we do apply, and apply needs an M of an A as an input, but we know how to create an M of an A, like an M of a leg or something. And we do apply again, and that needs an M of a B, but we know how to create one of those. And we do apply again, and that needs an M of a C, and we know how to create one of those. And that gives us the M of the result. So by doing this apply over and over again, we can take a function down here and lift it into a function up here. So let's look at some code. So here is our create body function. Very simple. In F#, to create a class or a type like this, all you do is just assign all the properties. So this is a creation function. And like I say, that's no good to us as it is. We need to work with M things. So what we'll do, And I'm going to use, instead of using the word apply, I'm going to use a special symbol, which is angle brackets with an asterisk in the middle. That means apply. So instead of a normal body, we're going to have an M version of the body, a lifted version of the body. So we start by taking this create body function, and we're going to return it up to the M world. And then we're going to do apply, which is the angle bracket thing. And we're going to apply it to the M version of the left leg, which is, we do know how to create one of those. We know how to create M things. And then we're going to apply it to the M version of the right leg, the M version of the healed arm, the M version of the right arm, the M version of the head, the M version of the beating heart. And the whole thing now spits out an M version of the live body. So we've got these M things, all the previous things we've done. So what we've done here is kind of interesting. We still haven't got any lightning. We haven't actually created any live things. These are all potential things. These are all promises to create things. But we're combining these promises to make a bigger promise, right? We're actually kind of programming with these M things. We're combining them in different ways. We're adding them. We're transforming them to create a new M thing. And that new M thing is still just a promise. But when we finally get the lightning, we can actually run the lightning on the entire body in one go. Right? We don't have to run the lightning on the various pieces and combine them afterwards. We can combine them in advance. And then when we get the lightning, we have the entire body ready to go, lying on the lab table, waiting for the storm, and then we can create the whole thing in one go. So if we do that, let's make it alive. So this is the output. So again, don't worry too much about the output. If we actually run it, we can actually see inside we actually create a live body. And the live body has a live leg in it, and another live leg in it, and a left arm, and it has a right arm which consists of two pieces, which is the lower arm and the upper arm, and then we have the head, and we have all these things are now live. So when we actually apply the lightning, when we apply the vital force, we've now created this live thing. And it contains a beating heart, everything. Everything we need is inside it. And what's interesting is finally, after doing all this creating, the remaining vital force is down to 2 units. We've actually used up 8 units in creating this thing. And again, it's actually keeping track of how much vital force we've used without having to say anything. So your brain is probably hurting a bit now. Like I say, it's all a bit much probably, but just if you can just get the concept of M things, that would be great. So let's just review what we've got. Do we have 2 problems now? The original thing was how could we combine these becoming alive functions and connect the output of one to the input of the next? Well, we've seen we can use apply, we can use bind. There is a way of doing it which is very easy without making it complicated. And then how do we take the various things that we create and glue them together? Well, we've got our map to function, and we've got apply. If we've got more than 2 things, we can use apply for that. So this is our functional design toolkit. I like to call them patterns. A lot of people in the functional community hate the word patterns because it makes them think of object-oriented patterns, but to me, they are patterns of how you use things. Or you can call them a toolkit. It's a set of things you can use to solve common problems. So here's our toolkit. We have map, return, apply, bind, map to, and so on. It turns out there's actually not that many things in your toolkit. I think probably about there's 5 things, maybe there's a couple other things you need, fold and traverse and so on. But really, it's amazing. One of the reasons that people like functional programming is there's basically 8, 10 things in your toolkit, and once you understand them, they actually work on everything. It's a very, very simple model. Once you get past the overhead of understanding it, everything falls into these patterns. And this leads us on to monads, and not just monads, but functors and applicatives. So now I'm going to tell you what a monad is. Okay? So I haven't mentioned the word monad at all, because I think monad is a kind of scary word. But you now know what a monad is, and you know what a functor is, because this map thing, a type like the M world with a map, that's a functor. And there's a couple of things. You have to have a sensible implementation. There's some kind of unit tests for the functor laws that make sure your implementation is correct. But given a sensible implementation and you've got a map, that's a functor. If you have this return thing and this apply thing and a sensible implementation, that's called an applicative functor. If you have a map to, that's a kind of a special version of that. And if you have a return thing and a bind thing, and you can put them together with a sensible implementation, that's a monad. So a monad is just a bind thing and a return. If you write those two functions, you've got a monad. So it's really a mysterious word, but you can see that the concept of bind and return, they're not actually very hard. So what we've done here in this talk is actually created the state monad. So the state monad is a special kind of monad that threads the state invisibly through all the code. And if we just revisit the code again, this was the thing where we created a beating heart. And looking at this code, you've no idea that there's state being, you're focused on the logic, right? It keeps track of the state. There was only 8 units. It figured out there was 2 units used up, but we didn't have to keep track of that in our code. So we don't have any obvious global variables, no obvious tracking things. Let's look at another one. Here's the final one where we created the entire body. And again, in this case, it kept track of everything. There were 2 units left. There were 8 units used up. Again, there's no kind of tracking variable to keep track of that. So this silently threading the state through is really a nice technique because it allows us to focus on the design. We don't really care about keeping track of all this stuff. I hate having variables which just keeping track of stuff when it's really kind of irrelevant to the main code. So by using the state monad, we can actually focus on the design and not on all these kind of technical details. All right, so finally, let's use these techniques in the real world. So Dr. Frankenstein was using it with body parts and stuff, but that's kind of gruesome, and most of us don't deal with that. But let's look at a real example, like a little web service. So people say, monads, they're kind of academic, they're too abstract, they're not really useful. So let's see if they really are useful. So here's a little web service where you update your user information, okay? So you input a little JSON object which has maybe your user ID and your name and your email, and you just want to update your address or something. So the first step in your web service is to validate the input. And maybe your name is blank and it won't let it, or your user ID is wrong and it won't let it, or whatever. And then the next step is to canonicalize the input, which means like trimming all the blanks, getting it into a standard format, trimming the blanks off the name, lowercasing the email, or something like that. And that always works. And then the next step is to fetch your existing record from the database. And maybe that might not work because maybe the record doesn't exist. And then the fourth step, maybe once you found your existing record, then you can update that record with the new information. Okay. So in pictures, how would this look? Well, the first step, the validation step, I'm going to represent it by some train tracks, and it's going to have 2 outputs, right? It could succeed and possibly it could fail. So I'm going to represent that as a 2-track model. There's a failure thing, which is the red thing, and a successful thing. The canonicalization is just a 1-track. It never fails, so it has the input and the output, and there's nothing wrong with that. When we try and fetch a record from the database, that could possibly fail, so I'm going to represent that with 2 tracks on the output. And finally, when I update the database, that's a dead end, because I just update the database and then I don't get anything back. So here we have a real problem. How do we take all these different shaped functions and glue them together into a nice function that we can work with? Well, what we do is we do the same thing we did with the M world, but now we're going to turn everything into 2-track. So we start with our normal world down here, and we're going to have a world of 2-track things. And we're going to turn everything from a normal thing into a 2-track thing. How do we do that? With our toolkit. We've got a map, we've got bind, we've got apply. All those things will take normal things into our 2-track world. So we have a single-track thing, we turn it into a 2-track thing using map. We have a thing which is a diagonal thing. It has a normal thing as input, but as a 2-track as output. That's a diagonal function. We can turn it into a completely horizontal version using bind. And then this last one, the more complicated one where it's a dead end, we basically turn it into a 1-track function by making sure that the output keeps going. And then we turn that 1-track function into a 2-track function using map. So we keep transforming our little functions, and after we start off with this, where they don't fit together, and after we've done all the transformations, we now have something where they do fit together, and we can now glue these functions together really nicely. So that's an example of a real-world instance of using map and apply and bind of all these techniques to unify our models so we can glue them together nicely. So that's the benefit of using monads, basically. So we've seen useful techniques here. Like I say, just really an overview. Hopefully, even just hearing about these techniques, and you can go away and look at them in more detail later. The main thing in terms of this technique is to turn these functions, this potential, this promise, into a thing. And we've started these M things. We've turned them into a thing that we can pass around. And that's a kind of interesting idea in functional programming where the functions become things themselves that you can manipulate. And the functional people like to call these computations or effects. So when you talk about people saying, I'm combining my effects, that's what they're talking about. Sounds a bit strange, really. I've shown you how to use map, apply, and bind. I hope that monads are not that scary now, right? Forget about the word monad and just focus on the bind and the return and all these things. But what's cool is we can work with all these effects, all these M things, without actually running them. We've actually built an entire object or an entire creature out of these parts, and we don't actually have the electricity yet to run it, but at some point later we can run it. So it's almost like writing a program. We're writing a program using all these techniques, and then we run the program at the very end, which is kind of strange. You're using programming language to write a program in your programming language, But you can actually think of it like that. And then we also saw the state monad where you can thread the data invisibly through. So very cool. No globals, no mutable state. So please do try this at home. Unlike the Mr. Frankenfunctor, you can actually do this safely without hurting any people. And I think that's it. Thanks very much. It's live, of course. If you're interested in the code, search for Monadster, and you'll find my blog post about it. And if you want to know more about F#, there's F# here. Thanks very much.